And the unit 3 talks about the ligand substitution reaction in square planar complexes. And the unit 4, which talks about the substitution in octahedral and tetrahedral complexes. So these are the 4 units that we'll be talking here in unit 1. And then we'll go for other units. So first we'll start with the reaction mechanisms in substitution reactions. So in this unit, we'll talk about the different types of substitution reactions. We'll talk about inert and labile complexes. They understand the mechanism of substitution. We'll follow the kinetic consequences of different reaction pathways, and predict the mechanisms of substitution in TBP complexes, that is trigonal uh, bipyramidal complexes. So first we'll define what is a substitution reaction. So as the name implies, substitution reaction means we are substituting something. So where does this concept first arise? It actually, the inorganic chemistry, it gained prominence during the Second World War. And mostly inorganic uh, chemistry, particularly the coordination compounds, they are unique because of two factors. The first factor is they have a greater degree of complicated reactivity, and second is they have a very wide variety of complex geometries. So that is why coordination compounds, that is particularly inorganic metal complexes, they we see a wide variety of complexes, and they are like plentifully available in literature. This inorganic complexes. So we can categorize them into three groups. So first is the substitution at the metal center. The second is the oxidation reduction reaction, and the third type of reaction is reaction of the ligands that do not alter the attachments to the metal center. So in order to test the different theories of the coordination geometries or of the coordination complexes, the geometry of the different types of coordination complexes, Werner and Jorgensen, they prepared particular certain type of complexes. So, to understand what type of reaction they undergo, what type of reaction mechanism are followed by the inorganic complexes, so two scientists, they prepared particular specific complexes. So, transition state theory was first proposed to define the particular structures, properties, and applications of such type of complexes. The transition state theory, it describes the chemical reactions as moving from one energy, that is which is at the minimum, through the higher energy structures, that is we call them the intermediates, to finally form the lower energy products, that is called as the products. So we know that this is generally how a reaction proceeds. That is, first the reactants, they react. So an in between state, that is before, that is the reactants have reacted and before the formation of the product, an intermediate state is formed, that we call as the formation of the intermediates, and ultimately finally the products it is formed. So these three states, that is the beginning of the reaction, the formation of the intermediates, and the formation of the products, they are all associated with different levels of energy. So and we know that these different energy levels, they have been represented by energy diagrams. So this free energy change that accompanies the reactions they have been shown with the help of a reaction coordinate diagram that we know. And here in figure 1b, like this is the energy profile diagram that we know from general chemistry. So here what we do is, if we take for example the substitution reaction, this is an example of a substitution reaction where mx plus y, that is they are the reactants, they undergo substitution reaction to form the product, that is my plus x. So when we look into this type of reaction, what happens is, here the in figure 1.1 you can see this is the energy profiles and the intermediate formation. So in the figure 1.1a, so in the x-axis the extent of reaction is taken, the free energy is taken in the y-axis. So here at the beginning there is a particular certain amount of energy of mx plus y, that is the reactant. So when they react, the intermediate state, it is higher, it reaches a value, and then what happens is After reaching a value, then they particularly this value that we called it as the threshold energy, this value, then it gradually comes down to form the product, that is it forms the substitution reaction, it occurs, and then we can see that the product has been formed as my plus x. So here in this diagram you can see that there is delta g. So this delta g is the free energy that is associated with the process. Delta represents the change in free energy that has been associated with the product minus the reactant. So in this first figure, this is a typical energy profile when there is no intermediate is formed. That is, it reaches a maxima and then it comes down for the product. But when an intermediate is formed, then we can see how the reaction profile it changes. So here in the second diagram, you can see this is the for the intermediate is the mxy, after which the product is formed as my plus x. So this is the general way how a substitution reaction and the energies that is associated with it are described. So numerous characteristics related to the reaction mechanism, they have been mostly understood by the kinetics experiment. Now, what are these kinetic experiments? Mostly kinetic experiment is when we perform an experiment of the extent of the reaction versus time, that is how much the reaction has progressed with respect to time, that is we'll take a time interval of either 5 minutes, 10 minutes, 15 minutes, or depending according to the nature of the reaction. So such type of plots or representations, they are called as kinetic diagrams, and the experiments are called as kinetic experiments. So whenever we have the term kinetic, it implies the rate of the reaction with respect to time. So and rate of the reaction always means the change in the concentration of the reactants or the change in the concentration of the formation of the products with respect to time. So we see the extent of reaction or the rate of formation of the product and the time. These are the two important factors which help us to know about the substitution reaction. So the free energy, we know delta G is a free energy, which is also affected by the nature of the reaction, that during the substitution reaction, temperature is also important, because we know that delta G is given as delta H minus T del S. So temperature also it affects. If we change the temperature for a particular reaction, then also we can see the change in the rate of the reaction. And also we know that it has been established that when we increase the temperature of a reaction by 10 degrees, then the rate constant it almost doubles up. So thus we can see temperature is also an important factor that affects the rate of this substitution reaction. Now, when a reaction is thermodynamically favorable, so how do we know when a reaction is thermodynamically favorable? This is the very basic law of thermodynamics, that is when delta G is negative. So if delta G is negative, then a reaction is thermodynamically favorable. And if delta G is positive, then the reaction is not favorable or it is not feasible. So when a reaction is thermodynamically favorable, then it may be slow if the energy of activation is very high. But when the reactions are thermodynamically unfavorable, that means delta G is greater than zero, which means delta G is positive, then a fast reaction may not occur. So in this case, we remember the Arrhenius equation, so which states that K is equal to Arrhenius constant capital A into exponential to the power minus EA by RT. So where EA, it represents the activation energy, R is the universal gas constant, and T is the temperature at which the reaction occurs. And it should always be remembered that the temperature that we talk of, it should always be taken in kelvins. So here in this figure, these are the reaction coordinate diagrams that has been shown for different types of reactions. So in the first figure, we see for the figure particularly for the EA and EB, we can see the activation energy is much large. But here in figure C, the activation energy, if you see, then it is very less. So once the activation energy large means it implies that we have to supply some energy so that the reacting molecules they cross the threshold energy, or they have to pass through this activation energy to form the product. Now when we see what does the rate law, we'll now talk about this rate law. Looking into the rate law, it tells about the nature of the reaction. Now substitution reactions in inorganic chemistry, it has been divided into four important classes based on the importance of bond making and bond breaking in the rate determining step. Now what is this rate determining step? We know that when we calculate the rate constant for a particular reaction, the rate determining step is the slowest step that occurs during the course of the reaction. So from that step, that is which is the slowest step, we can find out the what is the actual rate of the reaction, and that is why it is referred to as the rate determining step. So now we will look into what are the four different classes of uh, for different classes of substitution reactions, particularly in inorganic chemistry. We are not talking about organic chemistry substitution reactions, but we will look into the types of substitution reactions that are happening in inorganic complexes. So the first case of substitution reaction is associative reactions. So associative reactions, they are represented by capital A. So what happens here is the formation of the my bond. We will take the general equation, that is mx plus y forming my plus x. So the product that is formed is the my. So the formation of the my bond, it takes place completely even before the mx starts breaking. So this is, that means even the mx has not totally broken down, but the product that is my, it has already start formation. So such type of reactions, they are called as associative substitution reactions, or we just say them associative reactions. Then the second class of substitution reactions are the interchange associative. So this interchange associative is represented as capital I and subscript as the small a. So this represent interchange associative. Now what happens in this case? Even though the mx bond, that is the reactant bond, it starts breaking before the my bond formation is complete, but the bond making is more important than the bond breaking. So interchange is the difference between this ia and capital A is that, particularly in associative reactions, the before the reactant bond breaks, the formation of the my bond has already taken place. But in interchange associative, so although the mx bond, that is the reactant bond, it has started breaking, but the my bond formation has also been, it has the, that is the product bond, it has also been formed. But here what happens is bond and making is more important than the bond breaking process. And then the third class of substitution reactions are the dissociative reactions, and they are represented as capital D. So here the mx bond is fully broken before the my bond begins to form. That means, so before the product is formed, the reactant bond has to be broken completely. So once the mx bond is broken completely, only only after that the my bond it starts to form. So then the fourth class of substitution reactions in inorganic complexes is the interchange dissociative, that is capital D for dissociative, and interchange dissociative is id. So here the product bond it begins to form before the mx bond is fully broken, but in this case the bond breaking is important, more important than the bond making process. So here these are the four classes of inorganic reaction substitution reactions in inorganic complexes. So we will gradually read one by one. So before going to the different types of substitution reactions, we will first understand what is inert and labile compounds. Now, and why do they arise here in this concept of inorganic complexes? So the composition of the metals first coordination pair changes when a ligand substitution reaction takes place. So what is the coordination pair in a complex? The coordination pair is the part which remains within the square bracket. Like here in this case, this iron here, the we know that we represent the coordination complexes in square brackets. So the part of the iron that remains within these two the square brackets, that is called as the coordination pair. So when a substitution ligand substitution reaction takes place, then what happens is the metals coordination pair it changes. So one ligand we know, because it is a substitution reaction, then one ligand it is replaced by another ligand, and if there is another new ligand is possible, then the previous ligand it further undergoes substitution, and this is how a normal substitution reaction it occurs. Chemists have found a lot of interest in studying these reactions, particularly when aqueous metal ions, water ions, they are involved, particularly with the case of H2O, and when they are attached with metals like iron or nickel, then the substitution reactions they are very interesting. Like here in this case, this is hexa aqua nickel, that is NiH2O6. It is green color. So when we dissolve this compound in liquid ammonia, that is 6NH3, then what happens is it undergoes a substitution reaction. So the substitution reactions is the this H2O, the 6H2O ligands, they are completely replaced or substituted by the same amount or the same number of the NH3 ligands. So previously it was hexa aqua nickel, now it is hexa amino nickel. So you see the ligands that is present in the coordination sphere, they get replaced. So here the that is why it has been mentioned that the metals first coordination sphere changes. If you look into the second example, you see this is iron H2O6, that is hexaaqua ferrous. So here it is very pale violet in color. If we give a thiocyanate ion, that is SCN minus, then what happens here is one H2O it is replaced from the Fe, that is FeH2O5. One H2O is replaced and one SCN minus it goes into the sphere to form the H2O. So this is how the substitution reaction takes place in inorganic complexes. Now there is one scientist, Tobe, who designated complexes having substitution half-life T half, that is less than 30 seconds, as labile. So what is this T half? We all know what is this T half. T half means the time taken, that is the time that is required for 50% completion of the reaction, that is termed as T half. So as per this scientist, when the T half of this substitution types reaction it is less than 30 seconds, then such type of complexes they are called as labile complexes, and the complexes where the T half is greater than this 30-second, they are called as inert. Now these labile complexes and inert complexes, this they are associated with lability and inertness. So they actually show how fast a reaction occurs and how far a reaction it is, whether it is slow or fast. So whenever we have inertness, so that means the reaction, that is the T half of the reaction is very much longer. But when we say that the complex has very good lability, so it means that the T half of the reaction is almost, it is very small or less than 30 seconds. So this is how we define labile complexes and inert complexes. Now coming to kinetics of water exchange. So water in coordination complexes, we know water is a very common ligand, and particularly to study the kinetics of the substitution reactions, the complexes with water, it has been taken as an example. So when MH2OM, this is an example has been taken. It is involved in a ligand substitution reactions. Then very fast reactions takes place. For example, when we have HNO3, NaCl, H3PO4, KSCN, and NaF, when they are added successively to a solution of FeNO3 whole 3 dot 9H2O, then we see different types of reactions are occurring. So, for example, in equation 1.4, you can see this is FeH2O6 3 plus chloride minus. So what happens here is one H2O is substituted by Cl, and one H2O, this molecule, it goes out of the coordination sphere. Then this molecule again, that is FeH2O5 Cl, when it is substituted with a phosphate, then what happens here is this chlorine, it goes out, it is substituted with a phosphate. Then if we take this molecule and take this complex and react with another ligand, then we see such type of reactions are occurring. So we see how does this successive substitution reaction takes place, and we have to always remember that since water is present here, they are all very fast reactions. So the isotope effects of water exchange reactions, they have been studied, and the products of these reactions depend on the relative bond strengths between Fe3 and the incoming and departing ligands. So what happened is the isotope effects, it has been studied, that is here oxygen has been labeled, you can see the isotope of oxygen has been taken, that is O18, and this is how the bond strength and it has been the relationship it has been found. So if we look here in table 1.1, we can see the rate constants for such type of water exchange reactions. Here this is for the first complex, you see titanium H2O6 3 plus. We know titanium 3 plus, the electronic configuration is T2G1. Electronic configuration, it is derived from the looking at the type of ligands that is attached with the central metal atom, and then calculating the number of d electrons present in the system. So TiH2O6 3 plus, so titanium 3 plus is a 3D1 system. So 3D1 system, and we know that particularly in octahedral complexes, the d orbitals, they split into two ways, that is T2G and EG. Now here this titanium 3 plus is a 3D1 system. So between T2G and EG in octahedral complexes, T2G is lower in energy and EG is higher in energy. So the one electron that is present in titanium, it will go to the lower electron, the lower orbital. So the configuration for this titanium 3 plus is T2G1. So that is why here it has been written. We have in this table, the you can see the electronic configuration, it has been assumed that if you look into the coordination number, then the coordination number of all the metals has been 6, so it indicates an octahedral field. And what water, we know it is a weak field ligand, so that is why what happens is since it is a weak field ligand, it will form high spin complexes. So high spin complexes means how the electron pairing will be done in T2G and EG. It is mostly by following the Hund's rule. We know the high spin complexes or the weak ligands, they follow the Hund's rule. So first we'll find out the number of d electrons that is present in the central metal, and then this has been given in the third column in this table, and the rate constants has been shown. So we see that for many substitution reactions, the electronic configuration of the starting material, that is the metal central metal atom, is very important in deciding the speed of these reactions. For example, the rate constant for water exchange of magnitude for chromium H2O6 plus and chromium H2O6 2 plus, they differ by 13 orders. That is, if you compare these two, here chromium 3 plus, the electronic configuration is T2G3, but where chromium 2 plus, chromium H2O6 2 plus, then the rate constant is greater than 10 to the power 8. But here the electronic configuration is T2G3 and EG1. That is why, and this particularly this table, it shows that why the electronic configuration is important and how it is related to the rate constant. So that is why these complexes, even though we are assuming that they are all octahedral complexes, but the electronic configuration, it determines the rate at which the water exchange reactions will take place. So now let us understand what are labile complexes. So labile complexes are those that react very rapidly. So labile complexes we have defined where the T half is less than 30 seconds. So this indicates that labile complexes, they react rapidly and may exchange one ligand for another within the time of mixing the reactants. For example, CrH2O6 2 plus. The activation energy for ligand substitution reactions are very low. So activation energy low means the barrier is very low and they can be accomplished with a low amount of energy. So the criterion for lability, it may be taken as that the reaction half life, the time it takes for the concentration of the initial compound, that is to decrease by 50%, it should be less than 1 minute or less. We say that is 30 seconds. So complexes are labeled as inert if they react more slowly. But you should follow that inert compounds, they have higher activation energy for which the ligand substitution, they, and thus they react very slowly. Now once what happens is, if the activation energy is very high, then we need much higher energy to cross that barrier. And what happens is, they react very slowly and they do not resist this ligand substitution. So to understand this, let us take the example of a very common species, that is iron H2O5 fluoride 2 plus. This is a very stable ion. It has a large equilibrium constant of its formation, that is the Kf is very high even though it is labile. On the other hand, if we say hexamine cobalt 3, that is CONH363 plus, it is thermodynamically unstable. Here you see this is thermodynamically unstable, that is delta G0 has been shown to be less than 6. So here the cobalt, that is the hexamine cobalt, it reacts very slowly and the activation energy for the above reaction is high, is very high, leading to its inertness. So if you'd like to understand the behavior of chemical of any complex, we need to uh, study both the thermodynamic and kinetic parameters of the complexes. Then lability and d electron configuration. So when we are talking of inorganic complexes, the d electronic configuration is very crucial, because we have seen in the previous case that the d electronic, that is the particularly the electronic configuration, they define the how it affects the rate constant. So we will always look, there is a direct relationship, there is that how this d electronic configuration and lability, they are influenced by each other. So in table 1, we see that the rapid exchange takes place for chromium and copper, which is also related to their John Taylor distortions. So John Taylor distortions, that is that you must have previously studied, and it tells us about very symmetrical, unsymmetrical orbitals, and how strong distortion, weak distortion, and which cases there will be no distortion. So this is according to, there is a rapid exchange for Cr2 plus and Cu2 plus, because these are all studied from the John Taylor distortions. So particularly if we take the example of this water exchange, we can see that the ground state geometry, it is nearer to the transition state, leading to rapid exchange of the water ligands, with particularly in the case of octahedral complexes. Now Werner, that is who is called as the father of the coordination chemistry, Alfred Werner, he studied cobalt plus 3, chromium plus 3, platinum 2 plus, and platinum 4 plus compounds, because they are inert and more readily characterized than labile compounds. Because we know, particularly labile complexes, the reactions happen so fast. So, but that is why, uh, and their T half is less than 30 seconds. That is why some specialized techniques are needed to study their kinetics. On the other hand, the PT2 plus, platinum 2 plus, platinum 4 plus, such type of compounds, they are inert in nature. So inert in nature here means that they react very slowly and their T half is much longer. So that is why Alfred Werner, he prepared some compounds using PT2 plus and PT4 plus, and their inertness and lability, they were studied, and some relationships or general rules, they were drawn. So here, as suggested in table 1.2, here it has been shown, general rules can be given for inert and labile electronic structures. So what are the general rules for labile and inert structures? The inert octahedral complexes, they are generally those with high ligand field stabilization energies, that is LFSE. So we all know what is CFSE, what is LFSE. Specifically those with D3 or low spin D4, D5 and D6. These configurations, we know that they do not have electrons in the EG orbitals and at least one electron in the T2G orbital. So before talking about inert and labile compounds, so what I was telling before, it is always important that we know the d-electronic configuration of the inorganic complexes that we are dealing with, and particularly after that we will also know the whether it is a high spin complex or low spin complex, then and that can be known from the ligand, so according to the spectrochemical series. So here, so we know that when we talk about the ligand field stabilization energies, then particularly those with D3, if you look at D3 or D4, D5 and D6, they have no electrons in the EG orbital. So all the electrons for D3, D4, D5, D6, they are present in the at least one orbital in the T2G orbital. So Tobbe accounted for the lability of ions having an empty T2G orbital or at least one electron in the EG orbital by postulating that the unoccupied low energy T2G, it bonded with that of the entering ligand followed by the departure of the leaving ligand. Now in substitution reactions, there is a ligand that enters into the metal coordination sphere, and there is the old ligand which tries to escape or try to leave the metal coordination center. So because of the T2G orbitals, of the vacant T2G orbitals and one electron in EG orbital, so there is some interaction. So the D3 inert classification, particularly for here chromium H2O6, it undergoes water exchange very slowly compared to high spin D4. So that reacts slower than vanadium. So here we will look into table 2 and we will look here into the general rules. So for D3, low spin D4, D5 and D6, the reaction rate is slow, and the fast reactions, they occur for D1, D2, low spin D4, D5, D6. So some, and for strong field D8, that is square planar, that is slow reaction. For weak field D8, it is moderate reactions, and D7, D9, D10, they are fast reactions. That is, they are such type of complexes, they are labile. So this is the general rule that how we can relate the inertness and lability of complexes based upon their number of d electrons or the d configuration. So in order to relate the electronic configuration to lability, we can say that inert complexes are those with very high LFSC, that is D3, and low spin D4, D5, D6. Particularly the borderline case here is the D8 configuration. So for D8 configuration, both dissociative and associative pathways, these configurations, they occurs a ligand field contribution to activation energy. Hence, these configurations, they are kinetically inert. So other configurations with no LFSE, they are labile. So however, if we compare the complexes of particularly of high spin complexes of nickel with copper 2 plus, zinc and cobalt 2 plus, then the reactions become much smaller. So we should also remember that for a dissociative mechanism, the activation energy must be equal to or greater than the bond dissociation energy. So the LFSE is only one factor in determining this, and when we know the change in LFSE is small, other factors are also very important. And one of the important factors is the pi bonding that is involved in the reaction. Then coming to mechanisms of substitution. So the classification of substitution mechanisms for octahedral complexes, it has been shown here. The stoichiometric mechanism, like we have intimate mechanism for dissociative and associative, and we also have interchange id associative and interchange dissociative. Then there is SN1 and SN2. So SN1 is we have nucleophilic substitution first order, and SN2 is nucleophilic substitution second order. So we find that an intermediate having its coordination number lowered is formed at one extreme. So lower coordination number is formed at one extreme. So the ligand which leaves and departs, and this sort of mechanism is known as dissociation. So association means an intermediate with a higher coordination number is produced when the incoming ligand contributes to the complex. So what is this interchange? The interchange, it occurs between the two extremes, that is, but here as the one ligand enters the reaction, and as one ligand it leaves the reaction, so the intermediate, that is I, it lies in between. So when the degree of assistance is small and the reaction is primarily dissociative, it is called as ID, that is interchange dissociative. When the incoming ligands, it starts forming a bond with the central atom before the departing ligand bond is weakened, it is called as associative interchange, that is IA. So whether it is possible or not to detect the intermediates, but kinetic evidence suggests that IA or ID mechanisms are preferred labels and not as capital A or capital D. So they all, the capital A and capital D represent the whole mechanism, and IA or ID, they are also totally different mechanisms than that of A and D. So here the categories D, A and I, they are called the stoichiometric mechanisms, whereas based on activation processes that are associative and dissociative, it is called as intimate mechanism. So here we see two type of mechanism, that is when there is particularly the activation processes are involved, then it is called as intimate mechanism. Then coming to kinetic consequences of reaction pathways. So now we'll study some examples in which the rate law, it is used to propose the reaction mechanisms. The similarities in the energy profiles for associative and dissociative reactions, it has been shown here in figure 1.3. That is, this is the energy profile, and for the what are the similarities you can see, but there is the mechanism, although the product form remains the same, but the mechanism of these two processes, they are different. So first is two types of information we can see. The information used to propose mechanisms and specific reaction conditions should be known. So the first step is to critically examine the data for the new reactions. So each substitution reaction mechanism, that is D, I or A, will be described within its law. So first here X indicates the ligand that is leaving the complex here in Mx plus Y. Y is the new ligand that enters the complex here, and the after this the new ligand takes the place of X, and X it goes out. So first we'll deal with dissociation. So in that is dissociative mechanism. So in a dissociative reaction, an intermediate with lower coordination number, it is formed first after the ligand goes away from the complex. So then a new ligand, it comes in, and the possibilities here it has been shown. This is the mechanism of substitution. Here, this is the reacting complex. The here it X it goes slowly. This is the dissociation mechanism. Here X it goes away slowly. Then the addition of the Y ligand it occurs fast, and here the geometry here, that is the substituted complex. So two types of geometry, that is TBP, it has been shown here. Trigonal octahedral and trigonal bipyramidal geometry it has been shown here. So what happens is the reaction processes, here it has been shown here, that is Ml5x. The K1 is the rate constant for the forward reaction. K minus 1 is the rate constant for the backward reaction. So in this case, so the here the X is the ligand that leaves. So it is the ligand that goes away. So then Y is the new ligand that comes in. So here Ml5 plus Y, K2 is the rate constant for the equation and for the reaction, and it becomes Ml5Y. Now to these two equations will apply the steady state approximation. We know what is steady state approximation. This is a part of physical chemistry. So here applying steady state approximation, the equation, the rate equation can be given as the d of ml5 by dt, that is the rate of formation of ml5 dt, is given as k1 into ml5x minus k minus 1 ml5 plus x minus k2 ml5 plus y. Now where, how does this come? You all know this is all as the rate law, how we derive by using the law of mass action. So this is the rate of formation of ML5, and since we have used steady state approximation, we get 0. So here after we putting all this value, then we find out that the rate of formation of the product is given by this. So this is the rate law that has been shown here. So this is how steady state approximation it can be used to predict the rate law for a complex reaction. So it may be said that in order to predict a D mechanism, that is the dissociative mechanism, the conditions associated with the steady state approximation that are present must also be shown. So the rate of formation of ML5Y and the concentration of X, that is the ligand that goes away, it must be inversely related as it is indicated in the rate law. So a D mechanism on the basis of the derived rate law will be dependent on X and Y in a complicated way. Here it has been shown here. However, if we have different types of series, so we can see the different types of reactions that have been indicated by such type of reactions. So this is how desubstitution mechanism is explained by different type by steady state approximation theory. So we'll just take a break of 5 minutes and again resume with this chapter. So now we'll discuss the case of interchange reaction. So when we take the case of an interchange reaction, then it is seen that the octahedral 6 coordinate reactant and the incoming reactant, they occur in a fast equilibrium with an ion pair that is loosely attached during the combination process. So because this is a fast reaction, so that cannot be detected, nor we see any increase in the coordination number. So how this reaction is represented, it is given by this type of reaction, the same substitution type of reaction, and K2 is very very less than K minus 1. And so here, if we apply the steady state approximation, we also get the rate equation in this form. Then when we take the initial concentration of m0 to be this and substituting for y0 is equal to y, ultimately the final form of the equation comes to equation that has been the rate equation has been shown here. So here experimentally k1 we can know, then but the two variations on the interchange mechanisms, that is ia and id, they have been found. So it is very difficult to distinguish between them, and experimental uh, processes are also very difficult to distinguish between ia and id. Then associative reaction, so forming an intermediate with an increased coordination number in the rate determining step. So this is the reacting complex. So here addition of the y, so you see this is the pentagonal bipyramidal, so addition of the y here it takes place, then the the x is removed and y here gets in. You see y is present here and one x is removed, so this is the substituted complex. And here for octahedral wedge, here it has been shown two types of associative reaction, they have been shown for capped octahedral and PBP, that is pentagonal bipyramidal. So the mechanism can also be studied by the steady state approximation, and it has been found to follow this order. So now coming to substitution reactions of trigonal bipyramidal complexes. So in this section, we'll study the substitution reactions in TBP complexes, and we know that TBP complexes are with coordination number is equal to 5. They are very frequently prepared nowadays, but their kinetic and mechanistic studies have not been explored. So particularly various acyl cobalt tetracarbonyls with ppH3, they have been studied, that is FeCO4 ppH3, it has been studied, and there is there has been the kinetics has been tried to be understood. So particularly this is, we know this is a 5 coordinated system, that is TBP is 5 coordinated system. And so in such cases for PF5 and FCO5, so there is an interconversion between the axial and equatorial positions. The axial positions is given as A and the equatorial positions as E. So the studies on here, a pentacarbonyl iron, it has also described in previous inorganic classes. So particularly in ML5 systems, very fast axial equatorial conversions takes place, but MPOR3 complexes, they have rates that are found only by NMR studies. You see how the conversions it has been takes place here in this scheme. The pseudo-rotation mechanism has been shown, and how the equatorial positions, that is E and E dash, here you see this is the equatorial position E dash, and here it is E, they become axial. If you see, here is E and here is, if this is E dash and this is E double dash, here if we look here, this is E double dash and this is E dash. So how there is interconversion and how there is change, equatorial becomes axial, axial becomes equatorial, it has been shown here in this scheme. So this, there is a 90-degree rotation on the original structure. So this overall scheme we call it as the, because the positions has been changed, we call them as pseudo rotation. So here in figure also in equation 1.24, here is also this pseudo rotation, it has been shown how it is changed. Here the arrow mark has been indicated and the change has been noted. So for transition metal hydrides of the type HMP4, the ground state structure is a distorted trigonal bipyramid, and it can be pictured as a tetrahedral arrangement of p ligands around M with the H atom on the tetrahedral face. So here in scheme 1.5 we see a tetrahedral jump. It has been suggested where the H atom here, the H atom, you can see it jumps from one tetrahedral face to here and then again to the next tetrahedral face to an edge, and how it moves throughout the different faces of the tetrahedron. Even NMR studies have also shown that this is how the mechanism takes place in trigonal bipyramidal complexes. So this unit is finished with this part. So these are some of the questions on the unit 1. Then coming to unit 2. So that this is the reaction mechanisms in substitution reactions part 2. So here in this unit, that is the second part, we'll be dealing with particularly octahedral complexes. We'll talk about solvolysis, hydrolysis. Also, we'll talk about conjugate base mechanism, racemization reactions, and kinetic and Chillet effects. And is octahedral substitution reactions. So type of octahedral substitution reactions. So first is hydrolysis. We know hydrolysis means there is an involvement of H2O or OH. Substitution by particularly water molecule or OH minus is hydrolysis. Acid hydrolysis means the product is an aqua complex. We call this process as aquation. That is the addition of an H2O to the existing complex. Then is the base hydrolysis. So base hydrolysis means the product is OH. That is OH has been added to the existing complex. So here you see OH has been added. So once OH is added means it is base hydrolysis, whereas H2O is added into the coordination sphere, it means that it is acid hydrolysis or mostly aquation. So depending on the pH of the reaction, the product is aqua or hydroxo. So at a pH less than 3, the product is aqua, and at a pH greater than 10, the product is hydroxo. So at an intermediate pH, the product is a mixture of the two. So then the reverse of hydrolysis is annation. So then there is water exchange reactions and solvolysis reactions which occur here in different types of octahedral substitution reactions. So now coming to linear free energy relationships. It is LFER. So LFER, it relates the kinetic effects with thermodynamic effects. So we must know that there is a thermodynamic parameter which relates to the bond strength of a metal ligand bond. So kinetic parameter, it relates to the dissociation rate of the ligand. Now, whenever bond strength of a metal ligand bond is crucial for the determination of the dissociation rate of a ligand, then LFER it can be seen. So, in such cases, a linear plot of the logarithm of the rate constants of the substitution reaction versus the log of the K, that is equilibrium constant K, it can be obtained. So, when we look into the Arrhenius relation, we know that K is equal to A into e to the power minus EA by RT. So taking the log value, here we see ln K is equal to ln A minus EA by RT, and ln K is equal to minus delta H0 by RT plus delta S by R. This is the thermodynamic parameter. So here, whenever the pre-exponential factor, that is A, and the entropy change, that is delta S0, they are comparable, and the activation energy EA is dependent on the enthalpy of the reaction, then ln K and ln capital K here, they will be related in a very linear way. So if we get the linear log-log plot, it can be concluded that the thermodynamic parameter delta H has a significant effect on the activation energy. So here, this is the log K versus the log K, that is the log-log plot. And here we see how the activation energy of the reaction or the delta H has a significant role. So if the activation energy is high, then the natural consequence of a stronger link between the metal and leaving group, and it leads to a dissociation. So also here in figure 2.1, the log of the rate constant for the acid hydrolysis process here of CONH35X, here it has been shown against the log of the equilibrium constant. So that is, here the rate constant is always represented as small k, and equilibrium constant here it is shown in capital K. So that in table 2.1 and 2.2, here you can see in these tables we can see the effects of changing the incoming ligands on limiting the rate constants for annation and rate constant for particular substitution reactions. So here, if you look into table 2.1, the limiting rate constants for annation, that is CONH35H2O, and we change the Y ligand here, we can see the difference in the K1 values. Also, the difference for the nickel complex and the change in the ligands, we can see the K1, K2 values change for the with the change in different types of ligand. So here in equation 2.6 and 2.7, the pre-association mechanism, which is thought to be there for the annation of nickel H2O6, here it has been shown and the data has been shown here. So comparing from the two tables, we can see the ligand, the mechanism for the pre-association mechanism for the ligand exchange, it has been shown here. So in the following subsections, we are going to study different reactions for octahedral complexes, and with suitable examples we'll understand the mechanism. So replacement of coordinated water, that is the water H2O. The complex ion is formed from the hydrated metal ion in solution. It is called as annation. That we know, when water, when the entering group is an anion, it is called as an annation. Here in equation 2.8, you see bromide is taken here. So bromide enters to this place. So here it is an annation and H2O comes out. Also similar is the case for this type of molecule for the nickel complex. Water comes out here, two molecules of water comes out, and then we have the complex. Then is solvolysis. So water being the most common solvent, hydrolysis is the proper term. When solvolysis is the general term for any solvent, and when we use water, then it is called as hydrolysis. So here hydrolysis, both acidic and basic medium. Here it has been shown in figure 2.10 and 2.11. Then is the conjugate base mechanism. The conjugate base, we know this is this has been the conjugate base mechanism is actually it has been discussed in greater details in the later section. So when an octahedral complex has to give up one coordinated anion by hydrolysis at first, and then the incoming anion substitutes the coordinated solvent here shown in equation 2.12. Those square planar complexes, they have direct exchange of two anions, but square planar Pt plus 2 complexes have a similar pathway. So here you see CONH35Br plus NCS, and this is how the substitution reaction takes place. So that is, here in this case, water, in here it is water is added, the bromine is removed, and water it takes up this position. When NCS is given, and with the removal of this NCS, it goes here, and water it goes outside. So we can see the hydrolysis and annation, they occur in opposite direction. That solvent water replaces another ion, and then another ion, that is here the solvent water, it replaces the bromine ion. But in the second case, the second anion, it replaces the water that is present inside the coordination sphere. So we conclude that bond formation is not so important in the activation process. So let us now discuss the evidences regarding the mechanism of water replacement on divalent ions. So here in table 2.3, The rate constants for the reactions of MH2O6 with various ligands in aqueous solution, they have been shown. So in table 2.3, data is given regarding the formation of nickel 2 plus complexes from nickel H2O6 2 plus, where numerous ligands are used. So here we may look at the data and conclude we can conclude that a change in the incoming ligand, it leads to the change in the rate constants. So here we see if the ligand is substituted by other ligands, then there is a change in the log of k values, that is the rate constant values. Also we can see that the change in rate constants is also affected due to the charge. That is, if you see here CO2 plus, nickel 2 plus, Cu2 plus and Zn2 plus. So here the metal, the charge on the central metal, it remains constant, but the charge on the substitute, that is the ligand, it differs. It also affects the, or it also influences the rate constant. So here the both the charge on the on the metal and the charge on the ligands, they influence the rate constant of the substitution reaction. So when an entering group, that is the water, is not affected by a change in the central metal ion, and when the total, that is the aqueous metal complex ion, has the water substituted by another ligand, then the rate determining step is that in which the water goes away from the solution. So this mechanism is D or ID. Cobalt complexes, we know they show a strong tendency for this ID mechanism. So when the total complex may be in the initial and the activated form, here it has been shown here, the pseudo first order rate constant, it observed in the presence of a large amount of X minus, it should depend in a non-linear way on the concentration of X, here as it has been shown in equation 2.14. So the data regarding this anation reaction, that is the addition of the anion reaction, it also supports the fact that ID reaction occurs by this way. So let us consider a very typical case where intermediates of lower concentration, lower coordination numbers are found, for example, CO, CN5H2O plus. So here in equation 2.15 and 2.16, the rate constant has been given. The anionic substrate, it reacts with the anionic ligand. So the substrate here, it is anionic. You see, it reacts with an ligand which is also anionic, that is X minus. So the rate determining step, how will we know? It is the step where the water is lost to form the intermediate. This is the intermediate, that is COCN5 2 minus, which has been stable and it has also been isolated. So because of such type of reactions, there is a possibility of the D mechanism, not ID but D mechanism. So the rates of water replacement. So this is figure 2. Here it has been 2.2. It has been shown characteristic rate constant, that is in terms of second inverse, for the substitution of inner sphere water molecules in a number of metal ions. So if we look into the figure 2.2, where the first order rate constants for the substitution of inner sphere water molecules by other ligands on both transition metal and non-transition metals have been shown. And also this is figure 2.3. You see, this is the rate constant for the exchange of water molecules in the first coordination sphere of MH2O6 N plus. So here figure 2.3 shows that the constant was plotted against the number of d electrons and for the di and trivalent data ions of the first row transition series. So in this figure, the nature of the entering group, it do not influence the rate constant, which supports a dissociative mechanism. And the second case that has been observed from these two figures, it is that the metal ions here in both the cases, they can be placed in 4 reasonable distinct classes depending on their substitution rates. Now we'll refer to the group numbers that has already been taught. So class 1 is, this comprises ion of the periodic, that is group 1 and 2. So class 2 is the first row transition series, and particularly the M2 plus and the trivalent lanthanides, that is La plus 3. The class 3 is the rate constants between 1 and 10 to the power 4 second inverse. That is the trivalent metal ions, they react somewhat more slowly than divalent ions, that is B2 plus, V2 plus. And class 4, they are called as inert, where the rate constants, they vary from 10 to the power minus 6 to 10 to the power minus 2. So platinum 2 plus, it comes into this type of category of inert. So the rate of exchange of bound water is influenced by a variety of parameters that is related to the metal ion. Particularly, the ionic size is very important when we are considering the case of class 1 ions. So what are the class 1 ions? That is the periods of group 1, that is the group 1 and group 2, except beryllium and magnesium. So here particularly what happens here is the group here, the rate exchange, the ionic size is very important when we talk of class 1 ions. So with the decreasing size of the metal ions, the substitution reaction rate, it slows down. So this may be due to the fact that the effective charge on the ion or other some property, it may be the factors that are responsible for the decreasing rates. So similarly, has it has been found for group 2 and 12. So from figure 2.2, we see that the rate of Mg2 plus and Ca2 plus, they are much different. That is why, which explains their behavior in enzymatic reactions. So particularly from figure 2.2, so we can see where here is Mg2 plus and here it is calcium. So this particular peculiar behavior explains why magnesium and calcium, they have been used in different enzyme catalyzed reactions or in enzymatic reactions. So other than the ions of group 1 and group 2, such type of direct relation between the rate and ion size is not available. For example, chromium 2 plus, nickel 2 plus, copper 2 plus, they all have the same, almost the similar radii. But chromium 2 plus and copper 2 plus, they have been placed in class 1 ion category, but nickel 2 plus, it has been placed in class 2 ion category. So why is this so? This is because due to the fact that both copper 2 plus, we know copper 2 plus is D9 and chromium 2 plus is D4. They are having distortion in their structures where axial bonds are longer and weaker than equatorial bonds, and this is actually an effect of the John Taylor distortion. So their ground state structures, it is nearer to those in the transition states, making exchange of the loosely bound axial molecules rapid. Now we will see the orbital occupation effects on substitution reactions of octahedral complexes. So what is the effect of the orbital occupation on the substitution reactions? And for this we will just consider the octahedral complexes. So coming to the orbital occupation effects on substitution reactions of octahedral complexes. So both Basolo and Pearson, they first predicted that there must be some relation between the orbital d orbital energy and the fact that the complexes will be whether they will be stable or they will be inert or labile. So it has been considered that whenever a substitution reaction takes place, then the energy of the particular d orbital that is involved, it undergoes a change because there is this transition from the ground state in the complex. So this contributes to the activation energy in the substitution reaction to a great extent. So here the structure preference energy, these are the plots. So for an octahedral substitution reaction, such type of diagrams, they are called as SPE. So we should see from the figure 2.4 that a d electron, particularly we'll look into the d electron here. This is for a 2.4. We see that it may have trigonal, bipyramidal or square planar structures that are either low spin or high spin. So here particularly for d electron, if we see, so it may be either TBP or square planar depending on its nature of ligand that is attached to it, whether it is a high spin complex or it is a low spin complex. But for octahedron, only one option exists. So the high spin transition state structures, they are only taken so that the electron spin, it doesn't change. Certain important conclusions can be made from the structure preference, that diagram, that the of the octahedron. If it is less than some arbitrary value, then the complex is predicted to be labile. But if the SP is more than that value, then the complex will be inert. So in figure 2.4, the difference in energy between the octahedron and the possible transition structures have been plotted in terms of the angular overlap model, that we call it as the AOM parameters. So it has been found that a dissociative mechanism occurs in octahedral substitution reactions for complexes of divalent metal ions of the first transition series. So for the first transition state in this D mechanism, the assumption is that of trigonal, bipyramidal or square pyramidal structure. So also the complex may be considered as kinetically labile if one EG unit or less difference is between the octahedron and the 5 coordinate complexes. So the chemists have been found to be the such calculations, they have been related with the experimental data. From figure 2.3, all the high spin of D3 through D10 hexaequo complexes have relative abilities in the order, that is V2 inert less than Cr2 plus and followed by this order. If we try to explain the plots theoretically according to AOM and other theories, then we can conclude interesting facts. That is, we can say that the D3 ions should be substitutionally inert here from the SPE plots that it has been shown. That is, VH2O6, which is a D3 ion, so it is substitutionally inert. All the high spin D4 to D10 M2 plus ions, they are predicted to be labile by either pathway, that is through C4B or D3H transition state structures. Here in this table 2.4, the prediction of inertness and lability for octahedral transition metal complexes, it has been shown here. Next, let us concentrate on the SPE plots for the high spin of D4 to D10, and here it follows this order. So the predictions for low spin complexes with D4, D5, D6 configurations are that they will be inert to substitution whenever whatever be the pathway. Low spin D6 CO3 complexes, they are found to be quite inert towards substitution. Then is hydrolysis. So the hydrolysis of metal complexes under acidic and basic conditions, here it is discussed. So hydrolysis can occur here, we know both conditions, either it is acidic condition or it is basic conditions. So we have understood by this time that hydrolysis are the reverse of anation. Anation means addition of an anion. So the anation and hydrolysis reactions, they go in different directions. So according to the principle of microscopic reversibility, the results of the studies on the hydrolysis of here CONH35X here plus H2O. So what happens here is the X goes away and H enters here. So here that means the anion is removed, that is X minus, and H2O gets inside. The addition of X minus will be the addition reaction. But here if we look into equation 2.17, there is addition of water. So the X minus goes out, and thus this is the reverse of the addition reaction. And particularly for such type of reactions, the ID mechanism here, that is the interstate dissociative interchange dissociative mechanism, is preferred. Now figure from 2.1 that we have plotted the log plot, that is capital K is the hydrolysis constant and small k is the rate constant. So here also the equilibrium constant, and it is equal to K by K nation, and no intermediate for such type of reactions has been observed. We must also consider the steric factors for different types of octahedral substitution reactions. So if you look here in figure 2.5, this is a transition state model which can undergo hydrolysis. So here this is acid hydrolysis reactions of such molecules. It has been shown here. So in a table 2.5, there is a comparison of rates and stereochemistry for the equation of the equation of the cis and trans isomers of cobalt 3 complexes of the type here. It has been shown. So these are the cis trans isomers, and you can see the comparison of the stereochemistry, that is the formation of the cis product and the trans product, and the K values for such type of reactions. It has been given here. So some molecules after hydrolysis, we see that there is a change in their geometry. So it has also been suggested that the intermediate will builds up slowly. They are different for the dissociative or ID mechanism, and that is why they have different, their entropies become different. Now once their entropy becomes different, their geometrical or their geometries also change. So here in figure 2.7, the stereochemistry of hydrolysis of trans cobalt diethylene diamine AX, here it has been shown, that is figure 2.7. This is the stereochemistry of a substitution reaction of trans MEN2X by dissociative pathway. It has been, this is a whole pathway that has been shown here in this reaction. So it assumes a D mechanism. Now when the configuration here it is retained, then the reaction it has a square pyramidal intermediate. The intermediate it acquires a square pyramidal structure. But the change in stereochemistry is seen when a trigonal bipyramid becomes an intermediate. Now whenever an X is given up, that is here, whenever we see in the intermediate state X is given up, the three edges of the TBP of the intermediate, it will have 120-degree between the atoms which are ligated, and the entering group it can attack the edges with where the angle is 90-degree between the ligands. So since here there are three edges, so three possibilities of attack are possible. One of the possibility, it gives rise to two cis product having the here it gives rise to two cis product, but another it gives rise to the trans product. So this is the whole mechanism. It has been shown here in this reaction. The reaction pathway has been shown here. Then here in table 2.6, the predicted percentage of the products for octahedral substitution reactions has been tabulated. So it predicts the possibility of the different types of products by D or ID mechanism. Then coming to the CB mechanism, that is the conjugated base mechanism. So we have discussed that the nature of the entering group, it do not influence the rate of the reaction in a octahedral substitution reaction. But this is not the case when base catalyzed hydrolysis is done. Like when we have ligands like NH3, RNH2, R2NH in basic media, then the nature of the substitution reaction, it becomes sensitive to the nature of the entering group. We see OH minus is the ligand, but also these groups NH3, RNH2, they have some basic nature, and also they contribute to they affect the rate of the reaction. So here in equation 2.18 we see this is the general reaction. Then in the figure, we see the ligand metal interactions in the octahedral reactant and trigonal bipyramidal transition for substitution reactions of trans COEN to AX plus. This is the ligand metal interactions in octahedral reactant and square pyramidal complexes has been shown. So here we see that the base catalyzed hydrolysis, they have second order kinetics of the reaction, which made everyone follow that they have an A or IA mechanism. So here the entire mechanism, it has been shown with the example of pentamine chlorocobalt plus 2. Here it has been shown. So in this mechanism, the first and most important step is the removal of a proton reversibly from a ammonia ligand. So the conjugate base of the original complex is formed. So the mechanism is named as conjugate base or CB. But this steps, it happens much faster and then the second step. So therefore we use the steady state approximation and the rate, it has been found to be this. So other examples, it has been explained with the help of this type of reactions. These are the some of the common examples which explain the CB mechanism. Then coming the kinetic chillate effect. So when we take polydentate complexes, they are thermodynamically more stable than their monodentate complex because of this chillation or the chillate effect. So the reasons being that the loss of the enthalpy associated with the chelating ligand is much more and it gets detached as away as it may reattach as because the kinetic barrier is small. So these are some of the examples shown here. The dissociation here in equation 2.24, here if we look here, it must be slow compared to that for ammonia. The ligand ethylene diamine, it has to adjust by bending and rotating here. By bending and rotating, this is the ethylene diamine that we have taken, and it has to adjust by rotating and bending itself in order to take the free amine from the metal. But the reattachment here in this equation, that is 2.25, it occurs very fast. Thus we can see that because of this chelating effect of the ethylene diamine ligand, it reduces the equation reaction rates to a significant extent. So this is the influence of chelates on the reaction mechanism. That is racemization mixed reactions. So what are racemization reactions? Here is one suggested mechanism for racemization reaction. Here it has been shown. So intramolecular racemizations, they are seen in the case of tris chelate complexes for both inert and labile complexes. So here in figure 2.10, the intramolecular racemization mechanisms, it has been shown. So here you can see how it changes and how this with a trigonal twist, these are some of the mechanisms. So the last part, it shows that is the Ray and Dutt twist. It is shown around an imaginary C3 axis and we can see the configuration, final configuration, and this is how it looks like. So now let us take the examples of the rate constants for linkage isomerisms for chlorobenzene, which has found to be this. Linkage isomerism and racemization has found to be this. Though here we see similar mechanism of dissociation occur for linkage isomerism and racemization, but we see the rate constant are much different. So because the linkage isomerism, it needs a rotation about the CC bond, so it is slower. That is why it is 3 into 10 to the power minus 5. The isotope studies on the cobalt oxalate 3, it has showed that the O18 exchange for oxygens not bonded to the metal is much faster than for racemization. Even Baylor twist has the same transition state T3H, whereas that for Ray and Dutt twist, it is slower. So here, in this section, this is about mostly about the racemization. So with this, this second part on reaction mechanism in substitution reactions is over. These are some of the terminal questions. So you can go through the terminal questions. In tomorrow's class, we'll start with ligand substitution reactions in square planar complexes. So thank you for today.